Hello everyone, and welcome to our channel. I'm Yongjun Chen, a PhD graduate in geotechnical engineering from Central South University, and I'm pleased to share with you my valuable joint research experience as a visiting PhD student at Monash University, and hope the follows will help you understand my research activities. We know that the rock mass is composed of intact blocks and fractures as well as structural surfaces. However, in deep ground environments, the fractured rock is frequently subjected to various stress disturbances, which induced by hydraulic fracturing, blasting, excavation, osmotic pressure, and etc. On the other hand, the disturbance of thermal stresses which induced by geothermal gradients, fires, coal gasification, nuclear waste cannot be ignored, especially the geothermal gradient, which has been neglected in many studies in the context of deep earth environments. Under these conditions, the failure mechanism of fractured rock or rock structures becomes more complicated. The structural surfaces will weaken the rock integrity and mechanical performance to some extent. The engineering rock masses with defects are also exposed to frequent dynamic and thermal stress perturbations. It poses numerous potential risks to engineering activities and increases the cost of prevention, monitoring, and treatment in budgets. In Study 1, we have conducted the investigation of a fissured red sandstone with thermal storage potential subjected to descending amplitude low cycle impacts. DALC impact tests are conducted on the fissured red sandstone after thermal treatment utilizing a modified split Hopkinson pressure bar, and the point cloud data of the fracture surfaces from the failure specimens are captured using a high-precise 3D laser. The fractured surfaces are systematically characterized through an array of parameters, employing digital image techniques and statistical methodologies. Additionally, the analysis devolves into intricate mechanisms of thermal damage and fracture evolution. This exploration leverages the mineral and thermal properties, DM simulations, and strain energy density theory. Eventually, mathematical and statistical methods are applied to reveal the complex relationships between DALC mechanical parameters and the fracture surface features. We established relationships between the DALC impact mechanical parameters, including elastic modular, failure peak stress, failure strain rates, failure strain, and fracture surface parameters, including fractal dimension, joint roughness coefficient, second-order statistics of grain scale covariance matrix, and textural parameters including ASM, COR, ENT, CON, and the elevations parameter. We also simulated the evolution of thermal damage development in the specimen using DEM. The number of different types of cracks, internal friction angle, density loss rate, and fractal dimension at different temperatures shows evolutionary patterns with similar trends. In Study 2, we have conducted the investigation of fissured red sandstone after thermal treatment with constant amplitude and low cycle impacts. In this work, red sandstone samples after the same heat treatment as in previous studies were tested by XRD and STA respectively. The CALC impact tests were performed on the specimens using a modified split Hopkinson pressure bar, and the microscopic characteristics of the fracture surfaces of the specimens were examined using SEM. The effects of crack angle and temperature on the dynamic and fracture behavior of the CALC treated specimens were analyzed, with discussions focusing on some properties, some stress development, some damage, stress wave transfer behavior, and structural features. As shown in the left image, the fatigue strains and life diminish as temperatures rise and increase with increasing feature angles, while the strain rate exhibits an inverse behavior. Furthermore, the peak stress intensification and strain rate softening observed during CALC impact exhibit great prominence at increased feature angles. Tensile wave reflected from the fissure surface is the inherent mechanism responsible for the angle effect exhibited by the fatigue strains and life. The elevated density of fatigue and some cracks in the grain causes the formation of the compressor crushed zone, resulting in the growth of macroscopic cracks nearly perpendicular to the stress wave direction. Additionally, temperature exerts a positive effect on the ASM and CUR of the grayscale covariance matrix in SEM image, yet a negative effect on the ENT and CUN. The results of the above research have been published in the JRMGE and JEAs respectively, and I have also completed the data processing for my PhD thesis while at Monash University, which will continue to be published. Please keep me in the loop if you are interested. The primary objective of 3G Deep is to advance resource recovery in relevant field, with a long-term version of fostering technological innovation for environmental protection and the safe, practical extraction of resources from deep earth. Our efforts are concentrated in 4 main research areas. First, climate action plan. Second, unconventional oil or gas, renewable geothermal energy, and hydrogen. Third, new mining methodologies. Fourth, waste to wealth. Guiding all our projects at 3G Deep are the UN Sustainable Development Goals 7, 9, and 13. My time in the joint program at Monash University has been one of the most valuable experiences of my academic journey. Here, I made many new friends and broadened my academic horizons. I feel incredibly honored to have this opportunity to study and growing under the guidance of Professor Ranjith. From him, I have gained many positive life attitudes and invaluable research experience. I'm deeply grateful for his diligent and patient mentorship, as well as his thoughtful care in both my academic and personal life. This experience have a profound impact on my future, and I will cherish it forever. That's all. Thanks for watching.